Welcome back for more organic chemistry. To get things started, we're going to begin by discussing alcohols, and we're going to start by naming alcohols. So you're going to see that we're going to do each functional group. We usually start with naming and then talk about how different things can be made, how they can be used, and maybe individual things about that particular functional group too. So hopefully these are going to be sort of segmented by functional group, and you'll see things sort of loop back around to previous things that you may have already noticed. That's a good thing if you do. Okay, so OH groups, that's what an alcohol is, as most of you should know by now, are designated with the suffix of OL, suffix being the end of the word. So what we do is we look for the longest chain. You would name that just like you do the alkane, and then replace the E at the end with OL. Now, I'll tell you this sort of as a spoiler. Whenever you're changing the end of the word, the very end of the word gets the lowest possible number when you're trying to number things. In a ring, that gets number 1. Just period. It gets number 1. So using that approach, let's look at how to name these. So this first one here, I have to find the longest chain. I should have said this earlier, with the OH in it. So we want to go up like that, right? So that's where I'm getting the octanol from. 1, 2, 3, 4, 5, 6, 7, 8 carbons in that chain. And when we're looking for the OH, where to put that OH, since it gets OL on the end, because that would be octane. We take off the E and put OL, so octanol. Since that's the end of the word, we need to put this as a number 3 substituent. So that gets the lowest number it can. That octanol, you can put the 3 in front of the term octanol, or you can break up the middle of the word and say it's a 3-ol. So that is another convention that says, well, if I've got 2 different functional groups, we can sort of tell them apart, which we'll get to here in a minute. But in this case, the 3 would mean that that's with the OL. In either case, we have a 6-methyl for that methyl group that goes in the front. And so either of those names should be just fine. Moving on, we have a chain here that has 1, 2, 3, 4, 5, 6, 7 carbons. Now this is what's known as an enol. So if I were to name that chain, instead of naming it as an alkane, I would name it as an alkene. So this would be heptene, Heptene. So again, we would take off that E and instead put on OL. Well, so an enol has both a double bond and an OH in that chain. Thing is that we then have to be able to tell people where each of those functional groups is located, right? So the EN, being not the full end of the word, has a lower priority than the OL, which has the higher priority. So that gets the lowest number possible. So we would do this 1, 2, 3, 4, 5, 6, 7. And that means that the double bond gets the 5 and the alcohol gets the 2. Well, here's where we have to break up the word in order to be able to tell the difference. Because if you were to say 5,2-heptenol, that wouldn't make any sense. So what we have to say instead is we have to say 5-hepten-2-ol. Because that says that the 5 goes with the E and the 2 goes with the OL. Okay? Now don't forget that when you have something with only 2 substituents coming off of that double bonded carbon, and there are in opposite carbons that there is that substituent, you need to identify that as cis or trans. If you have 3 or 4 substituents, then you need to use the E and Z nomenclature. You can still have R and S types of substituents. So here we see this is R4-methyl-2-pentanol. because this would be 1, 2, 3, 4, 5. Just as a reminder, our prioritizing when it comes to labeling the priorities around the carbon here that is your chiral center, that is different and that is separate and apart from your chain. So I'm putting in a different color so you can see that. OH would be a number 1 priority. This would be number 2 over this side. Number 3 would be that carbon, and remember that the hydrogen in the back would be 4, so we don't have to worry about that. This is going to go to the right, and therefore that is an R. As I was noting earlier, if you've got an OH in a ring, that OH is in position number 1. You can put it in, you don't need to. So this would be an example of 2-isopropyl cyclopentanol. Why? Because we've got 1 right here. That would give that the next lowest number. And in the second example, we could go either in either direction in order to number, but if we go in the first direction I indicated, that will give each of these a number 2, and this one is 6. And you might say, why is it that I need to have 2 of the number 2s? Well, the reason why, this is a trimethyl. You don't know where those methyl groups are. One could be on 2, one could be on 3, one could be on 5, or you could have, like we have here at 2,2,6. You have to tell people where each of those are. If you were to say 2,6-trimethyl, that says there's only 2 of them, not 3. Okay? So make sure you put those in. There are 2 common names to know that we use quite frequently, but actually this is used in IUPAC nomenclature as well. So this is known as phenol. Now it's really easy to put that as in like language terms, something very similar to a phenyl group. So I overpronounce the OL on purpose. I call this phenol. That is different from a phenyl group. So phenol has an OH. Benzyl alcohol is one that just has a carbon right there. That's the only real difference. When you go to name these, I put a little example to the side. You have to assume that at the phenol position, that is position number 1. Again, you don't need to label that, that's understood. That means that this would be number 2. There we have number 3. That becomes 3-methylphenol. Okay. A couple other things. So we can designate alcohols with different types of designations. We call this a primary alcohol, as you see right here. Why? Because the carbon that's attached to OH there has one other R group coming off of that, and that R group could be anything that has carbon in it. Probably other things too. Haven't really seen that much though, just so you know. This would be secondary. There's 2 groups coming off of it, and here we've got a tertiary alcohol because it has 3 groups coming off of it. Diols are also a thing, and we're going to see how to make those here in a minute. But you have to tell people where both of those OH groups are located, just the same way that we needed to tell people where both of those methyl groups were located. So for example, this is 1,3-cyclohexadiol. So this would be 1, 2, 3, or you can number it the other way. It's the exact same thing. And this would be 2,4-heptanediol as an example. Okay, other substituents can definitely be in there as well. So do be aware of that. Alcohols can be deprotonated. They can be deprotonated by something with that is a really strong base. So we're going to talk about hydrides soon. I believe that'll be in the next video. But a hydride is kind of a way to stabilize H-. So hydrides can do that. There's the word written out for you. Or you can also do this with something like solid sodium or lithium to remove that hydrogen. So you have to have something that's a really strong base to remove that oxygen in general. What that's going to make is now oxide ion. So that's what that is called when you have that negative charge there. Now, something to note here. We should be able to identify patterns so that you can tell, given a range of molecules, which one's most acidic or which one's most basic. And the same rules applies to what we've looked at before. If you have resonance possibilities, then it's going to make the conjugate base more stable. So remember that when we're looking at the acidity of a particular set of molecules, what we really want to look at is their conjugates and which one's most stable within those conjugates, right? So things that would be most stable are something with resonance structures. So where there's charge dispersal that is actually taking place amongst different atoms holding a negative charge. Okay, that's the most stable. The least stable would be where you have an oxygen with a negative charge that is pretty much just on that oxygen. And that oxygen is taking all of the ownership of that negative charge. Okay. In between, we have inductive effects, where like fluorine in this case is able to help pull the electrons towards it. So that basically is going to pull the electron density to the other side of the molecule, which will give some stability to that negative charge on the oxygen. It helps the oxygen out a little bit, okay? So I kind of look at it this way. If I have a charge, or if I am in the middle of a field and I fall and break my ankle, well, I don't want to have to deal with that by myself. I'd much rather have friends around, and those friends, kind of like these fluorines here, could kind of like let me at least lean on their arm or something as I hobbled through the field to get to the car and go to the hospital. Now, this example doesn't really work in this case, but if one of those friends would be so kind as to take the actual broken ankle themselves, that would kind of be like what resonance would be like. That's not even humanly possible in this example, but you see my point here is, I hope, that if you're taking all of that charge just upon yourself, it makes more burden for that particular atom to hold. And so it's not as stable. And so the more you can disperse that out, the better off you are. Resonance is king. After that, inductive effects happen. And then, yes, there is this third category to simply say that if you're going to be in a situation like this versus in a situation, and that's chaos, sorry about that, a situation something like this, where solvent cannot access this oxygen as freely as it can this oxygen because there's more space around it, then that can't be stabilized as easily. So that's a really small type of thing, but it does actually exist as well. Now, remember, we can resonance stabilize that phenoxide ion. So here's how we do that. I drew for you the different resonance structures. So these electrons from oxygen can come in. They then go up to the next carbon over, and then we sort of just take that on throughout this ring. What that allows us in the end is to see that most of the negative charge is still going to be on that oxygen because there's two resonance structures with a negative charge there. But we also have resonance structures with partial negative charges, or negative charges. The resonance structures can move to those locations. So the hybrid would have partial negative charges at those locations as well. Not all locations, specific locations. And that is something we're going to look at a lot when we look at what's known as EAS reactions. So those reactions are the ones that involve benzene. benzene is its own thing. The reactions that work for everything else do not work on benzene, and vice versa. So you almost have to just put that aside into a total separate realm of existence and know that that is in its own category. But we'll deal with that when we get there. And next, we're going to look at different types of reactions with alcohols, making them, using them, etc. Thank you.